So each of your groups had an opportunity to look at one of these algebraic structures and figure out what were the orders of the elements that we worked with here. And what do you notice looking across these four different examples of multiplication tables? I've written the orders of elements that you came up with over here sort of on top of the list of elements. What do you notice? So there are two great observations. The first one is Grace looks at all these numbers and says, well, hey, all the orders that we got were either 1, 2, or 4. That feels like it could be meaningful. So all element orders, I want to be very careful here, all element orders in every example were either 1, 2, or 4. And then Caitlin says, the different group is obviously different. Right? Which was the different group in this list?
The A, B.
Yeah, this one here in the middle, the set symmetric difference. The different group had a different list of orders. 1, 2, 2, 2. So what is the fundamental disagreement here between the different group and the others? So what would be a quick and simple way to say why it is that this group is different from the other three using the idea of element order? So G3 is different because why?
It doesn't have 4.
Yeah, because G3 does not have an element of order 4. Whereas all three of the other examples do. And so this is a really powerful way of distinguishing between different groups. Right? If I can know the orders of all the elements in my group, then that's going to give me a lot of information and a lot of potential disagreements between that group and other groups that we might be studying. What do you think is the import of the observation that all the orders of our elements were either 1, 2, or 4? What are 1, 2, and 4? What do they have in common? How might they be related to these groups? Why should it maybe... Why might we know in general what orders we can expect there to be in a group without doing all the calculations? What do you think is the relationship between 1, 2, 4 and the setting in which we're doing these computations? I guess the question I'm trying to get to here is, what is the order of these groups? Not the elements, but the groups. What did we say a few minutes ago? 4. So, do you think there's a relationship between the orders of these elements and the orders of the group?
Those are factors.
They're factors of 4. So, how might we describe this? The order of an element of G and the order of the group G in the case where these are finite. So you'll notice that in these examples, we only have a finite set of elements to work with, and so we're going to have a finite order for the group. Also, it turns out finite orders for the elements. But the result that you're postulating here, Kenzie, is that the order of an element of a group G is a factor of the order of the group G. So that is worth drawing a large, colorful box around. Because this is the kind of statement that seems like it would have a lot of legs in abstract algebra. Right? This is a kind of statement that would seem to constrain quite a bit how many different structures that we can have for a given group if I know how many elements you're giving me to work with. Right? I can make a Cayley table, but if this result is true, my Cayley table needs to reflect only that the order of every element of my group is a factor of the order of the group. If this thing is actually true, spoiler alert, it is, but it's going to take us another 4 or 5 weeks to actually see a proof. We need to build up some more structure. But this is a good conjecture, a good expectation for now.